Welcome to Winchester Cafe Scientific. Tonight's speaker is Professor of Geoengineering and Carbon Management at the University of Southampton, a post he's held since spring 2013. A key focus of his research is on developing novel methods for removing carbon dioxide from the atmosphere to mitigate global warming. He's working on field trials for CO2 removal by direct air capture and by enhanced rock weathering and mineral carbonation. He's one of the co-founders of the startup company 4401, which is the 2022 recipient of the Earthshot Prize from the Royal Foundation. He received his MSc and PhD from ETH-Zurich in Switzerland. Please welcome Professor Juerg M.
Thank you very much for inviting me, and it's a great pleasure, for me to be here and discuss a little bit about my research. And as you can see here on this slide, my life is not that great, so it is actually quite exciting, especially what I will talk about today. Or to this evening. So the title, I slightly changed the title, to rapid carbon dioxide capture and storage via mineralization and enhanced weathering. But it's basically the same, we look or we will discuss some kind of different way. I call it an unconventional way to take care of anthropogenic CO2 emissions. And here, you can see on this slide, you can see kind of the anthropogenic perturbation of the global carbon cycle. This is a natural cycle, where carbon is cycling from different reservoirs, like the ocean, like the terrestrial, biosphere, like from the rocks, and obviously, through human activities. We produce a lot of carbon from the rocks, which is fossil fuel, which has been stored, for millions of years. But what you can see here is kind of the average global perturbation in gigatons of CO2 per year from 2010 to 2020. And the fluxes are basically, the important fluxes are in this purple color. And on this graph, which is from 2018, it's a little bit older now, in terms of the budget, but it's 34 gigatons of CO2 are released by our activities into the atmosphere per year. Some of that CO2 goes back into, for example, the surface ocean. It goes into, the biosphere where, trees and the plants are taking CO2 up from, the atmosphere. But as we'll see in a minute, a lot of it stays in the atmosphere and accumulates in the atmosphere over time. And that accumulation basically, produces kind of a man-made greenhouse gas effect. It makes our, the Earth warmer. That's what we call global warming. So here you can see the global total emissions, CO2 emissions, the annual CO2 emissions. Now, a projection from 1960 to 2020. And you can see the emissions from land use change. That is basically, deforestation, and change to agricultural land emissions from agriculture, but it's mainly deforestation. The good news here is that it's pretty stable. It's not increasing, it's actually a little bit decreasing. And you can see the emissions from the fossil fuel burning. This is basically our combustion of fossil fuels, which are the dominant part. And here you can see in red the total emissions. And as you can see, they increased over the last decades, from 1960 to 2020. And they're right now, I showed you the numbers, from 2018 on the previous slide, but they are now roughly above 41 gigatons of carbon, CO2 per year. That's a lot, no? So this is a huge volume of CO2. Where is that CO2 going? This graph basically shows you where it is going, where there are minus numbers here. This is basically a sink of that CO2 from the atmosphere. And where it's positive numbers, it's basically emissions. So these are the fossil emissions I showed you, and these are the emissions from land use change. But if we focus on the minus numbers, it is basically, 26% of that CO2 we emit annually into the atmosphere is directly absorbed by the ocean and stored in the ocean, dissolved in the ocean water. 29% is basically stored, taken up by the biosphere and stored as biomass. And 48% stays in the atmosphere and produces that global warming effect we see. So today I will discuss, one of a potential solution to take care of this 48%. Here you can see where, the emissions are coming from now. So you can see from, that's the BP statistical review of the world energy 2020. And it's difficult for you to read, but basically the different colors are: green is the oil, what is the world primary energy consumption? The green is oil, the red is natural gas, the gray is coal, and then we have the renewables up there. And this is just, 2020, and, the decline here is because of the pandemic, which we can ignore right now because it's going up again. All are going up. But the good news here is basically shown here is that oil consumption is decreasing. Coal globally is decreasing. Natural gas is increasing. And the renewables are increasing too. And that's what we see in this country too. There is a change in primary energy or the providing the primary energy, is more and more coming, especially for electricity from renewable sources like wind and solar. So this is good news, but still, if we look globally, the majority of our primary energy demand is satisfied by fossil fuels. And that won't change in the next few decades. So that's why, we have to find a solution to mitigate the climate effect of this fossil fuels. So here you can see by source, just very quickly, these are fossil CO2 emission by source of fossil fuels. The dominant one are still 40% is from coal, from 32% from oil, and gas is 21%, and the cement industry is providing, of all this 41 gigaton of CO2, 5%. So what is our job? Our job is pretty clear, and you can see that here it is on this graph. It's greenhouse gas emissions in gigaton of CO2 equivalent per year. And you can see, the time axis here to 2100. And so to stay below 2 degrees Celsius involves, a kind of a substantial net negative emissions. So we have to take CO2 out of the atmosphere to stay below 2 degrees Celsius. And, the Paris Agreement was about, to stay roughly for the warming goal at 1.5 degrees Celsius. So this might be, we will most likely not meet that Paris Agreement 1.5 degrees Celsius. But to stay below 2 degrees Celsius, this is the blue curve. You can see that by 2090, we need negative emissions. And I will discuss what that means. That basically means we have to take CO2 out of the atmosphere. If we stay at business as usual, then we will have warming that's way above 2 degrees Celsius with all its environmental impact. We already start to experience now. But I have to before I start to talk about carbon dioxide removal technologies, I have to really make the point that this gray part, avoided emissions, which is basically, a big part of that mitigation can be done by avoided emissions with conventional mitigation technologies. What do I mean with conventional? That means that we switch, from fossil fuels to renewable energies for primary energy demand, like electricity. We insulate our houses better. We change, our transportation fleet, to more sustainable way of transport. So there's a big part we can contribute without technology I discussed with you today. This is very important, no? But what I discussed with you today can contribute, but it's not the only solution. It can be an important one. So what is, in terms of this reduction of emissions, what are our options? No? What can we do? We can do two things generally. We can reduce emissions or we can increase carbon sinks. These are the two options we have. Reducing emissions, as I mentioned just before, we can increase efficiency of our energy systems. We can change the fuel mix from, as I mentioned, from fossil fuels to more renewable ones. We can substitute, renewable energy sources for fossil fuels. We can, and the UK goes in this direction. We can, build more nuclear power plants, and other countries are not going in this direction. Or, we can also do carbon dioxide removal, which basically includes taking CO2 out of the atmosphere and store it somewhere. And today I will discuss one option, how we could store CO2, and that's via mineralization. And then on the carbon sink, we can do something called, enhanced weathering. We can stop deforestation. We can do reforestation, and we can do some other things, which I will not cover today. So now I will focus on how can we store CO2. When we take it out of CO2 out of the atmosphere, how can we store it? What can we do with it? And actually, the geology shows us what to do. And it's called, the weathering cycle. So over geologic time scales, CO2 is basically consumed by weathering. So it reacts naturally with rocks. It weathers the rock, and which I symbolized here, with silicate rock weathering. So this is basically, not going into detail in chemical equations, but this is a calcium silicate mineral. Reacts with CO2 and water and produces, dissolved CO2, which then later reacts, calcium carbonate, and calcium carbonate is limestone. So what the geologic weathering cycle does, it takes CO2 out of the atmosphere, it dissolves rock, and that rock is then converted, mainly silicate rocks, into something like limestone. And the net removal of this is basically 1 mole of CO2 for each mole of silicate minerals. If I take, that calcium silicate mineral here. It's an efficient process, but only, on geologic time scale. And unfortunately, we can't wait thousands to hundreds of thousands of years. The problem is too big, too urgent. So we have, in my research, what I do is basically, I try to engineer that natural cycle, the weathering cycle, and speed it up. This is the product, no? You can go to the Dover Cliffs. The Dover Cliffs, that carbonate is basically the product, of CO2 that was, absorbed through into the oceans, and through the weathering cycle, the carbon combined with calcium, magnesium, and deposited over geologic timescale this chalk we see in the Dover clefts. So what I do in my research is basically I take certain type of rocks, react them with carbon dioxide, and convert this carbon dioxide through this reaction into stone, and the stone is similar, to the Dover clefts. So how do we do that now? So we take, this calcium and magnesium silicate-rich rocks. I symbolize it here with two minerals, which are olivine and pyroxene, and these are just silicate minerals. These silicate minerals react with CO2 and water, produce, another silicate mineral called serpentine here, and calcite. And calcite is calcium carbonate, is limestone. And the rock that is rich in olivine and pyroxene, which are both calcium, magnesium, silicate minerals, is called peridotite. And I will explain that a little bit more, in a minute. But if I take, the peridotite mineralization capacity, I can, we can calculate that a ton of rock, a ton of this peridotite, take care of 500 to 600 kilograms of CO2. So to convert 600 kilograms of CO2, I need a ton of rock. You might say, oh, that's quite a lot of rock. But there are million tons of this rock on Earth. Another type of rock you might be more familiar is called basalt. Basalt is basically, what you find in the Giant Causeway or, in Iceland. And it's a volcanic rock. Similarly, basalt consists of, this type of minerals, silicate minerals. The capacity of basalt is a little bit smaller. It's 170 kilograms of CO2 per ton of rock. But, just to explain a little bit more of this rock, so peridotite you usually find in the mantle of the Earth. That means 40 to 60 kilometers below the Earth's surface. The whole mantle of the Earth is basically peridotite. In some places, that peridotite was, through tectonic forces, was basically brought to the surface. And that, one of that place where I work a lot is in the Sultanate of Oman and the United Emirates. And there, we have peridotite on the surface, as you can see here. And in this tiny image, so all this black rock is mantle peridotite, usually, 40 to 60 kilometers below, but now on the surface. And because it's usually below the surface, it's not in contact with water, it's not in contact with carbon dioxide, and that's when it was brought up to the surface, it's like a chemical battery. It's in disequilibrium, with water and CO2, and it immediately reacts. And the reaction product you can see here in this really nice, beautiful pool, this blue whitish water, but it's whitish because that water, when it comes out of the rock, it is very alkaline. It means it has a very high pH of up to 11 to 12. And that absorbs CO2 directly. It sucks CO2 directly out of the atmosphere, precipitates that CO2 as calcium carbonate, as limestone, which you find in these pools. Similar here, but basalt, it's just an illustration. This is the Giant Causeway, in Northern Ireland, or this is, an example which looks a bit different, which is like a layer, a black forest cake, so it's layers of basaltic flows, which is in the northwest of the United States. Another example of this natural product of mineralization, you can see here, this is from Oman again. All this white rock is calcium carbonated. It forms these beautiful terraces on these mantle rocks, but this is all, absorbed CO2 that reacted with these rocks and was deposited as calcium carbonate as limestone. So you might ask, oh, do we have enough rock? No, so I just told you that we need tons. No, we need million tons of this rock. So here you can see a global map, and in purple are the oceanic, basically igneous plateaus, which means, you know, it's basaltic and peridotite rocks. You can see basically every continent we can find this type of rock. There are larger ones, like here in the northwest of the United States, the Siberian traps, the Paraná basalt in Brazil. But you also find them in the oceans. So the ocean floor is basically, you know, all basalt. So there is a lot of basalt, and if we look at the theoretical storage capacity of these rocks, and that I emphasize it's theoretical, no, it's not technologically feasible to access all that capacity. But you can see that, you know, in the ocean ridges, which are these yellow ones, it can have up to 250,000 gigatons of CO2 stored. That's more than all the anthropogenic CO2 emissions. But, you know, it is theoretical. That's kind of important to realize. And peridotite also has a huge capacity. So the message here is we are not short of this type of rocks. We have to figure out how can we engineer it. So how do we plan to engineer that? You know, this is a schematic, basically from my colleagues in Iceland, where we did the first mineralization test in basaltic rock. So you would have an emission source, you capture the emissions, or you capture CO2 directly from the atmosphere, which is called direct air capture. And you basically then inject that CO2 into the deep subsurface, below 800 meters. So very deep. You can do that on land, or you can do it offshore as illustrated here. There are right now kind of two companies pushing that mineralization technology. One is the Carbfix in Iceland, where we did, you know, initially in 2012 to 2016, the first test of mineralization. This is now a company. We do it on a commercial scale, and we have, you know, my startup company, or I'm a co-founder of it, 44.01, where we do, you know, pilots in the UAE and Oman. So this company is dealing with peridotitic rocks, you know, this mantle peridotites, and obviously in Iceland, it's basaltic rocks. So what I will show you right now is, you know, the initial results, because they were very key for developing and basically proof of concept. I show you what we did in that Iceland project, which was called the Carbfix project. So there, we injected very small amounts of CO2 to see what is happening if we inject CO2 in this type of rock. So we injected 175 tons of CO2 from January to March 2012. And, you know, we injected another, you know, 73 tons of CO2 and hydrogen sulfide mixture in June 2012. This was, you know, just the project organizations. At that time, you know, I was at Columbia University in New York. That was before I basically came, you know, to England. And we had University of Iceland. Reykjavik Energy was our industry partner. We had the University in Toulouse and the Icelandic Geosurvey. Everything was paid by research grants from the US Department of Energy and the European Commission and the Nordic funds. So here you can see what we did. This is just outside of Reykjavik. I don't know if some of you have been, you know, in Iceland. So this outside Reykjavik, 30 minutes. This is the Hellisheidi geothermal power plant, 350 megawatt power plant. They produce electricity for Reykjavik, and they produce hot water for Reykjavik. So how do they do that? It's a geothermal power plant. They produce geothermal steam from the subsurface. That steam had CO2 in it, CO2 and hydrogen sulfide. So we took the CO2, you know, we captured the CO2, we built a pipeline, and we injected that CO2 here into these basaltic rocks. And we just basically looked at what's happening. So this is a pilot scale project. So here you can see the power plant. Here you can see our injection borehole. So we drilled boreholes and we injected the CO2 through this borehole into, a salt formation between 400 and 800 meters. And then we had some other boreholes where we could do observations downstream of the injection borehole. So what is happening what's the fate of the CO2? That was the big question. Here you can see a schematic, what we did. And this schematic here basically shows you we have an injection borehole where we injected the CO2. And we have an observation borehole where we took samples from that depth and we measured certain things. We measured also, how much CO2 do we get in that observation borehole. So you have to imagine that from the injection borehole, the CO2 traveled in the subsurface over that observation borehole. But because we were only, below 400 to 600 or 800 meters below surface, at that depth, CO2 would still be a gas. And so you have to go much deeper. And then, if you go deeper than 800 meters, CO2 changes its density because pressure is increasing the deeper you go. And it converts towards a supercritical fluid. But that was not our case. So we had to come up with a different solution. So we co-injected wastewater from the geothermal power plant. And we co-injected water together with the CO2, both mixed in the borehole. And when fluid entered the injection formation, we basically had a single fluid, which was a sparkling water. But that sparkling water, had a pH of 3. So that means it was very acidic. And that acidic water immediately reacted with the basaltic rock, dissolved, calcium and magnesium ions out of the silicate minerals. And then, we did observations what is happening, when that dissolution occurs. In order, to know what's happening, we added some traces, we call that traces, into the water stream and into the CO2 in order to basically track our injected fluid in the subsurface. So these are chemicals. These chemicals are non-reactive. And this is, the key part, which it might be a bit complicated, but I will walk you through. So for the monitoring, we basically added in the water stream, we added a dye tracer, like a color. But that color doesn't react in the subsurface. So we can easily measure it if we retrieve a fluid sample from, the injection interval. And we also added something called, like radiocarbon. But, I know this is radioactive, but, we added radiocarbon on a concentration that is basically similar to the radiocarbon concentration of atmospheric CO2. We could do that because any carbon that exists in our reservoir at 400 to 600 meters has no radiocarbon. It's too old. The reservoir fluids and the rock are too old to have radiocarbon. So, we packed, so-called packed, our injected CO2 with radiocarbon. And then, in the gas, we added some gas traces, which are, sulfur hexafluoride is one of it. But basically, all these chemicals were added to see what is happening with the CO2 during the reaction. So again, I just want to emphasize, think about that we injected here solution and we pumped fluid out of the reservoir here. And then, what I show you now is results of the fluid samples we collected here in that observation borehole as a function of time. So here you can see a so-called tracer breakthrough curve. So this is now from this observation borehole as a function of time. No? So this is days since the start of the injection. And in blue, let's just look in blue, the blue diamonds. And this is the so-called, sulfur hexafluoride tracer, which is non-reactive. That tracer, that chemical does not react with rock. It only gets diluted by mixing between our injection fluid and the fluid that exists, the groundwater that exists in the formation. And you can see here after 60 days a little peak. Concentration, increased, decreased, and then increased a lot. And we had the highest peak concentration of these traces after 400 days after the injection. What does that tell us? If we look at fluid flow in reservoirs, that told us that the majority of our injected solution approached our monitoring well 400 days after injection. So think about our plume I showed you, arrived at our observation borehole 400 days after we did the CO2, started the CO2 injection. Here you can see now, let's focus on the red circles now, dots. This is the dissolved inorganic carbon. So this is the dissolved CO2 in our sparkling water. The concentration of the CO2 in our sparkling water. You can see a peak again at 60 days now, similar to what we've seen with tracer. Do you see a peak after 400 days? No peak. Disappeared. There was no carbon in there. So that's, the first indication something happened with our injected dissolved CO2. This data, can be used to do calculations, and I don't go into detail into these calculations, but all this data can be used to do a mass balance calculation. So basically calculate how much mass mass of CO2 reacted with the rock, or was mixed with groundwater. So conservative traces as sub6 was used to calculate the mixing between our injected water and our groundwater in the reservoir. And then we can calculate the CO2, dissolved CO2 concentration we would expect if we have only mixing, no reaction. And it's this, we can do that with these equations, and then we can basically calculate the difference between what we measure in the sample we get out of the reservoir at the observation borehole and the one we would expect if we only have mixing. And you can see in red is basically the concentration of the dissolved CO2 we would expect if we just have mixing, pure mixing, nothing else. Huh? We would expect after 400 days that much CO2, but from my previous graph we have not seen that CO2 after 400 days. So this is the measured data. So basically the measured dissolved CO2 was very, very low. The concentration in the fluid of measured dissolved CO2 was very low compared to what we would expect if we just have mixing of the two fluids. So meaning most of the CO2 reacted with a rock. So what we see here, that was for the first time, we could prove that CO2 reacted to dissolution with basaltic rocks and was precipitated as calcium carbonate down in the reservoir. No? So we had basically, this was the proof that 95% of the injected CO2 mineralized, was converted to stone. How do we know that now? So people criticized us, you show us an indirect proof, but do you actually have calcium carbonate in the reservoir? Which is a difficult proof, no? Because we drilled the borehole, we retrieved rock cores, but a reservoir is very, very big, and a borehole is just a needle in the ground. So to find CO2 that go mineralized in the rock down in the reservoir is very difficult. But we had some samples, and these samples, these carbonate samples, we measured, this radiocarbon concentration. And that radiocarbon concentration was actually the concentration of radiocarbon in our injected CO2. So this was the direct proof that CO2 was mineralized, was converted to stone, to calcium carbonate. It also, in our observation borehole, we observed that all our equipment got scaling. A pump failed, for example. But that scaling all had, that radiocarbon. So basically, yes, there was mineralization happening in the subsurface as a consequence or as a result of our CO2 we inject. So this was, very big headlines, and I don't know, back in 2016, if you remember some of the headlines, but there was huge coverage, in the BBC, in New York Times, and in other places. But basically, the more important part here is that through this research, we basically then allowed, this company, Reykjavik Energy, but now Carbfix, to further develop that technology and to commercialize it. And by now, in Iceland, they basically mineralize 80,250 metric tons of CO2 captured out of the atmosphere and captured from a geothermal power plant. Since 2014, that's what they mineralized. Still small, if you think about the 41 gigatons they make per year, but actually a significant contribution to further develop that solution. And, others also, which is kind of more a funny fact, for example, Bill Gates, his personal emissions, he buys, basically credits, from Carbfix to basically offset his personal emissions. So this is, what the Icelanders developed now. It's commercial, on a commercial scale. And it involves, capturing CO2 from this geothermal power plant, but it also involves, capturing CO2 directly out of the atmosphere with machines like a sketch here. These are kind of machines that absorb CO2 from the atmosphere, from the air, capture it, and both are basically then injected in Iceland into the deep subsurface where it reacts with salt and gets mineralized. We do similar things, with our startup company, and this is just, very small images. So we basically have direct air capture machines, in Oman, where we capture CO2 directly out of the atmosphere, injecting it into peridotite rocks. But the difference here is also all is run by renewable energy. The whole system is run by renewable energy, and the energy demand capture CO2 directly out of the atmosphere with these machines is quite significant. And so actually one way to go, and we think it's the only way to go, is that you power this with renewable energy. And that's what we do, with solar plants. So here, for example, where this little direct air capture machine is situated, you can see the roofs of our buildings are all, solar PV panels, producing the power we need. And we just finalized, in Fujairah, in the Emirate of Fujairah, our first injection site. So we drilled our injection wells. Injection will start on a 1 million ton scale in October this year. So there is, also an initiative going on in peridotic rocks. We proved that it works, not only in Iceland, but also in peridotites, but now we scale up. So this, what I showed you on the previous slide led, obviously, we were nominated by the Earthshot Prize, by the Royal Foundation, and we were lucky, you know, that we could win, you know, the 2022 prize from the Earthshot Prize from the Royal Foundation for, you know, the category of fixing the climate. And, you know, the prize will be basically reinvested into capacity building, a knowledge center in the Sultanate of Oman, to, you know, to basically educate and further develop our knowledge. So in summary, before I move to my last part, is, you know, mineralization eliminates CO2 with no leakage risk. Because you might ask the question, if I inject CO2 into the subsurface, you know, it can come back. Subsurface is not a leak-proof container. But if we mineralize it, no? Minerals don't leak out of the ground. It's not possible. No? I mean, you have to inject acid again to get it out. So it is really permanent storage. And that's, you know, since I'm, you know, was a young scientist and started this research in Columbia University in New York, my focus was find, you know, a permanent storage that has, you know, minimizes the risk of any leakage. And that, I think, is very important. And also, you know, the environmental impact should be very, very small. And, you know, converting CO2 to a limestone has a very small environmental impact. So that's basically the goal. No? So basalt and peridotite, the rocks are found all over the world. We have enough of these rocks, as illustrated, you know, by this capacity here. And what is really needed now is basically R&D, really upscale the R&D to develop, you know, that mineralization process further, bring down, you know, the energy or bring up the energy efficiency of the process, and also to develop efficient monitoring and verification of the mineralization. That is important because finally somebody pays for it, and the regulator wants to see that it is permanently stored. It's not leaking back into the atmosphere. So verification is very important. But there is also something else we can do. And this is something called enhanced terrestrial weathering and mineral carbonation. You can see here, you know, one scheme, and that's actually, you know, happening here in the UK too. Norfolk, they spread crushed basalt in agricultural fields. And what is happening, you know, with this crushed basalt, it weathers in the soil, it enriches the soil with carbon, which is absorbed from the atmosphere through CO2, and it basically stores, again, more carbon into the soil that got lost during, you know, the industrial agricultural evolution. And something else I'm interested in, you know, mining industry. Mining industry produces a lot of rock waste, but that rock waste is finely powdered now. It is basically very fine sand, as you can see here, you know, from one of the platinum group element mines in South Africa, and mine tailings, you know, from nickel, diamond, chromite, old asbestos mining are rich in calcium, magnesium, silicate rocks. So same rocks like peridotite and basalt, but are very finely crushed because the mining industry recovered the metals out of them. And here, you know, one example, a very extreme one, though, in this graph is basically the 1,000 million tons per year of rock waste produced by the mining industry. And one example is, you know, if for 1 gram of, you know, diamond, you have to mine 10 tons of rock, a lot of rock. And that rock, you know, where diamonds occur, is rich in calcium, magnesium, silicates. So that mine waste, what we are working on, could use that mine waste to basically react with CO2. And again, we go back to what nature is doing. And nature, here you can see an abandoned asbestos mine. You know, these are the tailings, basically the waste rock. Asbestos is out now, but it's an abandoned mine, Clinton Creek mine. And, you know, colleagues just looked at that mine waste and calculated that that mine waste approximately reacted with atmospheric CO2 and stored 160,000 tons of CO2 naturally. And this mine has huge capacity to store more, you know, CO2 if we could find out a way how we can mineralize that waste through reaction with CO2, and that's what we are doing. And here it's too small. You know, that graph, unfortunately, is too small, but it basically shows you in the y-axis the carbon dioxide removal potential in kilograms of CO2 per ton of mine tailings. And here you can see the estimated tailings production in million tons per year. And, you know, if we, for example, you know, look at the nickel mining up here, or, you know, we go to the diamond, kimberlite, we can then calculate, based on this mining data, that the theoretical carbon dioxide removal potential of this mine waste is about 1.1 to 4.5 gigatons of CO2 per year. So, you know, we have a waste product sitting around. We could make use of that waste product to actually, you know, tackle some of the global warming problem. And this is basically what we calculated, we published here in this paper, but there is a huge opportunity for the mining industry to actually make, you know, make mining carbon neutral. In addition, mining operations could take more CO2 out of the atmosphere than, you know, what they produce. So it could also be, you know, a business model for the global mining industry. But more important, you know, it is really kind of a waste product that is sitting around, and we could use it to mitigate global warming or global climate change. So what, you know, are our key findings? And we call that ex situ mineralization because, you know, you can't inject CO2 into the mine tailings. This is an open system. They are just hills, and, you know, on the surface, CO2 will come back. So global mining industry hosts large volumes of reactive mineral waste, so-called tailings. It could be the feedstock. So what we have to figure out is basically how can we bring that CO2 into this tailings, or how can we bring the tailings or the CO2 to react, you know, with these tailings. That we still have to figure out. You could imagine it could be something like a cement plant where you have tailings and the CO2 in a reactor are reacting with the CO2 and convert that CO2 into limestone again. And then you have to find a way, you know, to dispose that limestone or use it. You know? So this is an open question, how we would do that. Are pilot projects. So all the global, you know, big players in mining, like Anglo-American, like Rio Tinto, they are on it now. They try to figure out how can they use their mine waste to mineralize CO2. So it is a very hot topic right now in the mining industry. But our research is really, you know, at Southampton is to figure out how can we do that in an efficient way, and what do we do then, you know, with the limestone we produce. So with this, you know, I stop here, and I'm happy, you know, to take any questions. Thank you.
Lisa, you have some questions for Juerg?
Goodness me, what the hands going up? This could take a while. May not be the first one. There is.
Yeah, Mike, I've got a question about the carbon balance of these various schemes. In other words,
the amount of CO2 that you're actually extracting, how much energy does it take to extract that and put it in the ground and mineralize it, compared with the amount of energy that's produced to generate the CO2 in the first place? Because if it's more, then you're not winning.
Yeah, no, exactly. Very good question, Bob. So in a conventional carbon capture and storage scheme, you know, so we talk about 80 to 85% of CO2 avoided. No, so basically, what you have to invest is 20% or 15% of the energy, you know, for the capturing process and storage. There is the big part. It's in the capturing. You know, as I mentioned, capturing is very energy intensive, and that's, you know, but it's decreasing. You know, so with the generation, first generation, second generation, third generation technology, that the efficiency is improving. You know? So basically, if we look at life cycle analysis, it is roughly, you know, 80% avoided is still, no, that's kind of, so you invest when you know.
Sure.
Yeah.
How does the technology you described compare to the direct air capture being done by the likes of Climeworks in Switzerland and a few other?
You know, what we use in Oman for capturing CO2 out of the atmosphere, I don't want to advertise anything, but that's Climeworks. So you know, what we do actually, you know, 44.01 is focusing on it's direct air capture, but that's still, you know, I think for large scale, many years out, you know? So what we really also focus is on point source capture, because, you know, that's where we can have a big impact right now. So direct air capture, we need direct air capture, you know, for negative emissions. That's the way to go. But, you know, there is a long hanging fruit, which is basically, you know, the point source. A bit ignored, you know, in the headlines and in the newspaper, because everybody talks about, you know, direct air capture. But clearly, you know, we have to focus right now on point source and, you know, develop further that direct air capture. The direct air capture, you know, if we look at the company scenes, you know, there are many companies now founded and building, you know, operational systems in the direct air capture space.
I have a burning question of my own that I can't take much longer. Going back to the Icelandic setup you were talking about, how in the research phase they use sulfate fluoride for developing. Please tell me that that's not part of their measuring recording valuation model going forward, given that sulfate hexafluoride is worst greenhouse gas that makes methane look positively beneficial?
Absolutely no. This was only in the research phase. In the pilot scale project, it was used as, you know, a gas tracer, inert gas tracer. Absolutely no. This is not the way to go forward. So we and other groups develop other, you know, monitoring verification technologies that do not involve, you know, substances like, you know, SF6. Yes.
Can you elaborate on that a little bit as to how the actual measurement reporting is done?
So you know, we don't really need, you know, all these traces. I mean, we can use dye traces, and dye traces are, you know, very common in groundwater aquifer characterization. We can use other, you know, substances that are used are perfluorocarbons, but also not that good. But then, you know, there is geophysical monitoring verification. That's where we also go, but they have limitations in the sense that if we inject dissolved CO2 on, you know, on certain like seismic wave measurements, we can't see, you know, the difference between, you know, the CO2 and the fluid, because it's dissolved. It's a single phase. But right now, you know, in Oman, for example, we develop all kinds of, you know, physical and chemical monitoring techniques and in situ sensors in boreholes to measure what is going on. So we don't really need this extra chemicals. And if you think the cost of monitoring will go up using if we think we inject tons of CO2 per year or million tons of CO2, you can't add these substances. They're only good for research projects to really figure out what's going on. But for an industrial scale, CO2 mineralization or CO2 storage, we need other technology.
So when they're talking about 80,000 tons so far, that has been measured.
They use traces, but they use the dye tracer. But not a continuous injection. They did kind of spot injections and then see what's happening.
Another question. Is there a risk that when you are injecting CO2, it forms a calcite layer on the rock, preventing further reaction?
Yes, fantastic question. Yes, obviously, the issue is that the pore space or the surface area that reacts get basically deactivated, because you precipitate calcium carbonate. But the reservoir, the porosity and the permeability of the reservoir has to be high enough. So yes, in one part of the reservoir that is happening, and at the end, you basically fill all your pore space with calcium carbonate, and then you have to go to another reservoir. But that's on really large volumes. But in peridotite, it's another interesting process we observe. If you convert, peridotite, calcium carbonate or magnesium carbonate, there is a volume increase. And how is the volume increasing in the subsurface? So that volume increase produces a stress, and that stress is high enough to crack the rock. Okay, and so we call that in the research field reaction-driven cracking. So think about, or you can imagine that a mineralization front looks like you put a coal seam on fire in the subsurface. Now you have a carbonation front that just basically, goes through the rock reservoir, and that front is because of that volume increase in cracking, you produce new surface area, which reacts again and again. For that, we could prove that under certain conditions, this reaction-driven cracking occurs. Under different conditions, you basically clog up the pore space and business is done. You lose, basically. So it is really in peridotite, it's very critical that we probably get into that regime of cracking. So, think about that cracking is not, if that would be a follow-up question, is not producing earthquakes. It is really just cracking rocks, which means it is very, magnitude minus noise we can record. But it could help in what you described, that you produce more surface area.
And that doesn't have any issues for stability of building structures on the surface?
No.
It'll take a long time to get out of this call.
Yeah, related to that, I was going to ask, did I see 150 bar pressure mentioned there? That to me looked like cracking pressure. And then another question was, what was the temperature at the injection site that you're using in Iceland?
The temperature first. The temperature in Iceland, what we did in the pilot project, that was a roughly 40 degrees Celsius. What they do right now, Carbfix and Reykjavik Energy, they inject the CO2 that is captured from the geothermal power plant into the geothermal reservoir. So it's 220 degrees Celsius. And why are they doing it there? Because they co-inject hydrogen sulfide. they co-inject hydrogen sulfide because their initial interest was not CO2. It was hydrogen sulfide. Because if you've been in Iceland, you might remember that it smells of rotten eggs everywhere. Or you take a shower and you think, whoa, what is that? But they add that. So the geothermal steam in some plants have, up to 15, 20% is H2S. That's a pollutant. No? So the Icelandic government came up with legislation and they are not allowed to vent that into the atmosphere. So they had to find a solution, and they re-inject the H2S now. They capture it, separate it from other gases, re-injecting it into the geothermal reservoir. And they just add the CO2 to it because that was the co-benefit. Into this high temperature reservoirs because I showed you that we did a test of 73 tons of H2S and CO2 injection in a shallow system at 400 meters. And when we started that injection, injectivity after 1 week dropped to 0. So my idea then was, we clogged the borehole. And with some, inert minerals, iron oxyhydroxides. So we tested that with all kinds of things to get, the pore space back. We couldn't, but then, we flushed the injection borehole. What came out was a biofilm. It was all, bacterial mats. And so what happened in the shallow system, I told you it was 40 degrees Celsius. 40 degrees Celsius, it had, H2S, which is hydrogen sulfide, which is an energy source for bacteria. And we added CO2 to it, which is a carbon source. And boom, a bloom happened, no? And clogged our injection borehole. Then, Carbfix, the geothermal company, said, we have to inject that, into a high temperature field or a reservoir because there is no life. And that's what they do, but the direct air captured CO2 in Iceland is injected into the shallow reservoir at 40 degrees Celsius. And so now I have to remember, or you have to tell me again your first question.
Oh, for reference to 150 bar.
Yeah, 150 bar is just a value, so we know that depends on the depth. No, if we go at 800 meter step injection, like we do in the Emirates, we have roughly a hydrostatic pressure of 80 bars. So we don't need 150 bars. No, so we inject roughly, hydrostatic is at 80 bars, so we will inject at 100 bars. So it is, it depends at what depth you are in the reservoir, what pressure you need for injection.
I know it's the other side of the world, but Australia were heavily into mining, and they weren't very keen on global warming and things. So, is this being applied in Australia? Or you don't know because it's not?
No, I know of several initiatives in Australia. Australia is one of the biggest, supporter of conventional CO2 storage. So they had large projects, even offshore, of CO2 storage in sedimentary reservoirs, like depleted oil and gas reservoirs. But also the mining industry in Australia. Mining is very big in Australia. They're highly interested, and they're working on using that mine waste for mineralization. So there are big initiatives in Australia happening.
Another question.
Just curious about your name of your company.
Yes.
What's the significance of that?
So that's the molecular weight of carbon dioxide, no? CO2. I didn't come up with that name, no, that was my colleagues, in Oman came.
It's slightly tangential question. It hadn't occurred to me until you heard your fiction. The carbon is so much on the surface. Well, my natural kind of would be mixed through the earth. But you say that you go down very far and you don't find, and then suddenly you stop getting carbon. Is there a reason that that understood?
No. What I, what I said is, the carbon 14, which is the radiocarbon, is not at greater depth. There is carbon, at greater depth. So if we look at the mantle rocks, 40 to 60 kilometers, the Earth mantle has actually a lot of carbon in it, the big carbon reservoir. But what I said is that the carbon isotope of radiocarbon, that does not occur at greater depth. No?
I did understand that it was you also said, I thought, that you go down, you get the rocks which don't have carbon. I forget the name.
The peridotite, yes, yeah, that's correct. We don't see, we drilled, we have roughly 1,000 kilometers of core from the peridotite in Oman, and we only see, in the veins and in the cracks, we see calcium or magnesium carbonate down to roughly 150 to 200 meters, and then all the veins and the rock below does not really have obvious calcium carbonate or magnesium carbonate. That has to do, with the water circulation system, the natural rock. How does carbon get naturally into this rock? It's by rainwater. Rainwater that infiltrates does not infiltrate that deep.
But where does the carbon come from then? If it's on the surface, it's obviously come from outer space, and
No, from there.
No,
That came from the atmosphere, no? Or originally, you mean?
yes.
Originally, the carbon molecule. Oh, yeah, that's a good question, no? So can't really answer. Because, yeah.
While we're talking about soil carbon, you were talking about the farming, putting powdered basalt on fields and getting carbon back into the soil. But is that bioavailable? Because that sounds like a very inorganic, mineralized form of carbon, as opposed to an organic source which would have bioavailability.
Absolutely. What they do is they spread crushed basalt, and that basalt is then in the soil, is weathered, no? So that weathering process absorbs more CO2, but it's an inorganic process. And then, it basically dissolves the basalt, and you have calcium, magnesium ions. They either mineralize, to calcium carbonate in the soil, or it's exported into the sea by, the river systems. But no, it is not bioavailable carbon, but the basalt, they see some benefit for the plants. And, interestingly, in California, in the 80s, basically plant nurseries, they sold crushed basalt because it has a little bit of phosphate in it. So that, that's the added benefit.
Another question, somebody. Yes.
What about exploiting the ocean? Absolutely, no. I mean, you've seen that we inject dissolved CO2, no? In Iceland and also now in Oman. So you need a lot of water to dissolve, to dissolve a ton of CO2 in water, you need roughly, 20 tons of water, which, that ratio is not sustainable, as you can see. So obviously there is seawater. We can do it in seawater, and there is a lot of that type of rock is offshore. So absolutely, the future lies into going offshore for this. In addition to directly, but the bigger opportunities are offshore. Why is it not happening right now? It's too expensive. Everything that's offshore is more expensive than on land, no? And especially for pilot scale projects and accessibility, it has to be tested on land.
But carbon CO2 absorption in seawater is becoming a serious threat to a lot of marine life because it's raising the acidity, even fractionally. Just the kind of processes that produce mineral structures are working. So we can't rely on the sea water.
I mean, that's a very important point to realize, you know, if I may add. So I showed you the global carbon cycle, and 20-something% of the annually emitted CO2 is absorbed by the surface ocean, dissolved in the surface ocean. That results, you know, in the acidification of the surface ocean. So over time, that potential of the ocean to absorb CO2 is declining, no? And that's very worrisome. I mean, it's not only worrisome because of the ocean acidification effect on the living organisms in the ocean, but also that less of our emitted CO2 in the atmosphere will go and be stored in the surface ocean. So that's a big issue.
Do you have any more questions? If not, then I think we will wrap it up there. And that was a fascinating discussion. There's a lot I hadn't crossed before. So, yeah, Professor Juerg M, thank you very much for coming along and giving us a very enlightening talk tonight.
Thank you.